Okay, so let's start the second slide. I also changed the title a little bit. This classification, the classification issue on this slide includes many different approaches, which we have already covered, uh, including the multinomial logistic regression, LDA, QDA, naive Bayes, and KN, etc. Maybe this slide is not so complete as I expect. Of course, in the future, I will also append more materials. But basically, this is what we are interested in right now. Okay, and in the future, we will include many different approaches. Okay, especially I myself are also interested in the regression topics. So I will introduce more generalized linear regression. Okay, including some more machine learning oriented regression techniques. But now let's just focus on some slides I just edited here. Okay, so we have we have already covered multinomial logistic regression. So this is different from multiple logistic regression. Okay, when we talk about the multiple logistic regression, we are referring to more than one explanatory variables or more than one features. But multinomial means we may have many different types of response. Okay, not just the binary response. Maybe we have 3 types of response, or 4, or 5, or more than that. So we call this multinomial logistic regression. So I just gave you the website. It's also called categorical regression. Okay, similar to that. But never mind, here I'm talking about the interpretation of the coefficient. Okay, so sometimes we will use the softmax codings. I think I mentioned that before. This is just easier. This is just to make our interpretation more easily. Okay, so this is about the prior probability of Bayesian and the posterior. We mentioned that. Okay, so first is about the LDA, linear discriminant analysis. So basically, what we are talking about right now is about the FK of X. Okay, so this is about the posterior probability. Okay, so the problem is how to estimate the density of FK of X. So this is the very challenge job in applying the Bayes probability. Okay, so usually we have many different assumptions. Okay, so the easiest assumption is linear discriminant analysis. So what we are doing here is we have the simplest assumption, okay, FK of X. So that means we can assume that FK is following a normal distribution. Okay, the normal distribution, then we can just do some transformation. So I just made some slight modification. So here I just show you that we can plug in both uh, equation 4.16 to 4.15. Okay, so this is just the process of transformation. Finally, we can calculate we can get the formula of pk of x. Okay, pk of x, and then we can use the maximum likelihood approach, okay, to find the maximum of delta k of x. Okay, so maybe this is not so interesting in terms of the mathematical transformation, but anyway, what we are doing here, okay, is to find the optimal value, okay, optimal value to determine the classifier or the boundary for classification, okay, boundary for classification. So for example, like in this case, if k equals 2 and the pi1 equals to pi2, then we can determine the classifier. We call this as base classifier, okay? So if this value, okay, 2x times mu1 minus mu2 greater than mu1 squared minus mu2 squared, then we can assign an observation to class 1. Otherwise, we will assign the observation to class 2. So basically, we need to find the base classifier. So you can treat it as a country. For example, we have two countries, okay, with two inland countries. Okay, we have to find the boundary. Okay, so we call this the country boundary or country line. Okay, to separate these two countries into two different places. So similarly, this is also to help us to classify the observation and to see which area this observation should belong to. Okay, so finally, anyway, we need to find the classifier. So sometimes this classifier will be linear. Sometimes this classifier will be nonlinear. Okay, so if the classifier is linear, then we call this as a linear discriminant. Okay, so if the boundary of classifier is nonlinear, then we call this as a quadratic discriminant analysis. So what we mean by linear discriminant is a linear base classifier. If it's nonlinear, okay, it's nonlinear base classifier, then we call this as a quadratic discriminant analysis. Okay, so that's the difference between this linear and the linear discriminant and quadratic discriminant. Okay. Okay, so this is, we call this the base decision boundary. Okay, decision boundary, okay, or country boundary, whatever. Okay, so we have to find this boundary value. Okay, so this is an example. For example, we have a P1. Okay, so the another assumption of LDA, or linear discriminant analysis, that the LD assuming that observations within each class come from a normal distribution with a class specific linear common variance. So we mentioned that before. So if possible, then we can default case, okay, codings. Okay, so if you want to let's see. Okay, so now we have, if you want to apply the LDA to our data, here are some codings that you may reference, okay? So for example, if you want to apply LDA, so you can just use the LDA function, okay? LDA function, I think it should be exactly, but I think it's okay, we'll talk about the codings later, but remember it's a package of correct. It's a function of a correct package. I'm not really sure about that, but never mind. Okay, so what I mean here is, okay, now you can suppose we have a default problem, and then you can use the LDA function. Okay, so now you can see here LDA, and followed by default field balance student. Okay, so now suppose we are using the training data set. Okay, so this example is to perform LDA on the data in order to predict whether default or not an individual will default on the basis of credit card balance and student status. Okay, so now you can see this is the output here. Okay, so this is based on the training data. Okay, and if you look at the output, then you will see we have group means. Okay, so the group means is the data. Okay, that shows that the balance. Okay, with 1,726. Okay, average balance were for the default. Okay, for the default. The average balance is a little bit higher. Okay, it'll be higher. So you can see the customers that tend to default have average credit card balance of 1,726, and are more likely to be student than non-defaulters. So that you can see the 30% of non-defaulters are students, okay? And then there are 37% of defaulters are students. So you can see this is the output of groupings. Okay, so this is quite informational. Okay, so then you can check this output here. And also the output also generate the prior probabilities of the group. Okay. So this is quite intuitive because we just use the original data to calculate the prior probability of groups. So there's nothing difficult here. Okay. And then how can we use the coefficient of the linear discriminant? So now you can see we have estimated coefficient for balance, okay, is 0.0022, and the coefficient for student is negative 0.2554. Okay, so how can we use this? Okay, now you can see based on this, then we can generate the predicted values. Okay, so you can see if this probability, okay, you can see here, when this equation is that less than 0, the probability increases that customer will not default. Okay, so when on the other hand, when this value is greater than 0, okay, then the probability increases that the customer will default. Okay, so these results basically represent probability. Okay, so the higher the result of this value, that means the higher probability of default. Okay, so you can see the difference here. Of course, you can also replicate you can also regenerate the plots, okay, by yourself. Let's focus on the output here, okay, because this is more interesting. if you check the test data, so now we are using the LDA model. This is our estimated model. And now we replace the data with test data. Okay, so this is our test data because originally we are using training data. Now we switch to the test data and using the test data to generate the predictive value. So you can see based on this, then we can generate the confusion matrix. Okay, so here you can also see a different way of confusion matrix here. Okay, so this is the prediction. Okay, on the column here. Okay, column here, this is prediction value, and this is the real value, realized value. Okay, so you can see this is the. You can also calculate the probability. Okay, so then you can see we are using prop the table. Okay. Okay, you can read the explanation on the right hand side. Okay, so if we move a little bit more, then you can also calculate the precision. Okay, now you can see based on the LDA model, okay, the precision rate is 27.82%. Okay, only 28%. But if we are using logistic regression, okay, the precision was 34%. So you can see the difference. Also, you can calculate the specificity, okay, but this is not that important, okay. So what I mean here is, okay, if we are using LDA model, why the precision is lower than the logistic regression? So why is that? Okay, so this is what we are concerned about. Okay, so if we are concerned with if we are concerned with the precision of our model, then probably we need to tune up our model by adjusting the posterior probability threshold. So here comes the threshold again. So if we are really concerned about the risk of default, then we need to increase, adjust the posterior probability high to be a higher level. For example, we may set up the posterior probability for about 20% high risk. Okay, so if that's the case, then we can run the codings. Okay, so in this case, you can see here, we can use the codings to regenerate the results here. Okay. Okay, here we are. If you want to adjust the threshold of the posterior probability, then you can follow these codings. Okay, so that means tested.predicted.LDA $sign, we have a posterior here. Okay, so you have to specify that, okay, greater than 0.20, which is 20%. Okay, so if we have to specify the posterior probability greater than 20%, then we will turn it as a defaulter, and no otherwise. Okay, so this is how we can adjust the threshold of the posterior probability of default. Okay, and based on this, then we can regenerate the confusion matrix. Okay, we can regenerate the confusion matrix. Then the precision rate has been improved to 61.7%. So now it's becoming better than the logistic regression. Okay, so this is clearly improved and better than the logistic regression. Okay, so the key point here is you need to know how to adjust the posterior probability of default here. Okay, you have to specify the threshold. Okay, so this is about the linear discriminant analysis. And also, just like I mentioned, we also have a quadratic discriminant analysis because now we may have a decision boundary which is non-linear. Okay, if that's the case, then we need to use quadratic discriminant analysis. But when we want to run the quadratic discriminant analysis, which is QDA, then we have different assumptions. Okay, so that means the assumptions of observations from the K class is based on a different covariance metrics. Okay, so in LDA we are assuming that they are coming from the same covariance metrics, but now maybe we have different covariance metrics. Okay, but it's totally up to the number of observations because we need maybe we need more observations to help us to get more precise estimation of QDA. Okay. But on the other hand, the more complicated model like QDA may not give us a very good precision rate in our estimate, in our prediction. So it's the problem of a trade-off, okay, bias and variance trade-off. Because QDA needs to estimate a lot more parameters than LDA. However, LDA is much less flexible classified than QDA. So this is just trade-off. Okay, so you need to measure both ways, and then okay. So in the following are some mathematical derivation. So I will skip this, okay, and give you a conclusion about the quadratic discriminant analysis. So roughly speaking, LDA tends to be better than QDA if there are relatively few training observations. So reducing variance is crucial. Okay, so it depends on the number of observations. In contrast, if the training set is very large, in other words, if you have a large number of observations, then probably you can consider QDA. Okay. So in this case, the variance of the classifier is not a major concern, or if the assumption of a common covariance matrix for the K classes is clearly untenable. Okay, then you can consider QDA. Okay, so here is a comparison performance of LDA and QDA. Okay, so now if you look at the chart here, figure 4.9 here, you can see there's we have a base decision boundary. So this is in purple line. Okay, so you can see here, this purple line is a straight line. Okay, because now we are using the LDA. Okay, we're using the LDA. So we will see a straight line of base decision. Okay, so this is base decision. On the right-hand side, you can see the purple line, purple dashed line. Okay, is a curved line. Okay, so this base decision line is curved line, so that it will be better to use the QDA. Okay. And on the other hand, on the left-hand panel, the two Gaussian classes have a common correlation 0.7. Okay, they have a common correlation of 0.7 between x1 and x2. Okay, so as a result, the base decision boundary is linear, and that can be accurately approximated by LDA decision boundary. Okay, but on the other hand, on the right-hand side, we have a different correlation. For example, for the orange dot, x1 versus x2, the correlation is 0.7. However, for the blue dot, x1 versus x2, the correlation is negative 0.7. So in other words, they share different covariance. Okay, they come from different data structures. Okay, so in this case, we should use the quadratic discriminant analysis. So this is about the data type. Okay, you can see here this orange dot and the blue dot here on the left-hand side here. They share the same correlation. Okay, because you can see this is a linear here. So both data sets, okay, share the same correlation, but in this case, they share different correlations. So it's a problem here. Okay, so this is just for your reference. So how to estimate the value codings? Okay, sorry, I would append the codings. The codings for you, but I think I have okay, so this is for your reference. And then LDA and QDA. And then finally, we have a naive Bayes. Okay. Of course, LDA and QDA, we have many different assumptions. But for naive Bayes, maybe this will be more straightforward. Okay. So now we are talking about the classifier. Okay. But the classifier here is to estimate the f function of x. Okay, so what we are doing here by applying the naive Bayes classifier is that within the K class, we're assuming that the P predictors are independent. Okay, so if that's the case, then we can restructure, reformulate the mathematical expression in this way, because the P predictors are independent. So we can generate the Fk of x, okay, to be formulated in this way, okay, because they are all independent. So if in this case, then we can simplify our estimation. Essentially, of course, there are some other problems, but essentially the naive Bayes assumption introduced some bias but reduced variance, leading to a classifier that works quite well in practice as a result of bias variance trade-off. So this is the third approach to calculate the probability, okay, posterior probability. Okay, so here is the example. So this is a toy example. P equals 3 and K equals 2 classes. So you can try to compute the results in posterior probability estimate of this. Okay. There's a coding for you to regenerate the results. Okay, so let me show you here. Just a minute.